Now, factors that affect the rate of the reaction. We're going to look at each of these factors and how they affect the rate of reaction. First factor, remember we said temperature affects the rate of a reaction. How does temperature affect the rate of the reaction? Now we see a picture here that explains. Look at this carefully, it gives you some ideas. Take a minute, pause the video and look at this picture and tell how temperature affects the rate of reaction. Okay, I'll pause the video. Okay, now we see a picture here. This happens at night. This frozen, freezing here. We can see ice. Okay, so it is freezingly cold here, and this is at night. And you can see that this guy here is covered, and that tells us that the temperature is low. Because of that, he is inactive. You see on this picture, inactive service, right? And we can see that things are orderly in the house compared to this. Now, in this picture, we have high temperature, right? The hot sun, we see the hot sun right there. You can see heat from the food and the boiling kettle, and also heat from the pressing iron right here. And that tells us that temperature is high. And when temperature is high, temperature is energy, and that means there is more energy and there will be more collisions. So we see there is more collisions. We see there are more collisions here, right? Things colliding with each other, pets, food colliding with each other, and there's a disorderliness right here. Now, this tells us that the higher the temperature, the more energy particles have, and that means the more collisions, and that means the faster the reactions. Higher in temperature, faster reactions; lower temperature, slower reactions. There are other things you can deduce from the picture. Okay, the higher the temperature, right, there is an approximately the faster the reaction. So we see here that increasing the temperature by 10 degrees Celsius can cause the reaction rate to be doubled. That's how much temperature can affect the rate of the reaction. So sometimes we cook, and this explains why we heat many times in a lab. Most times we heat in a lab to speed up our reactions, because the reactions might not happen if we don't heat, or they happen very slowly if we don't heat. So temperature, one of the reasons why we cook, one of the reasons why we heat in a lab a lot of times, is because the increase in temperature increases the rate of the reaction. Okay? But what causes this? This explains that, like I just said, the higher the temperature. Now, if you're asked to explain this, you have to explain it logically. The higher the temperature, what does it result to? Particles gain more energy. Remember, particles are always moving and in constant motion, just like a bumper car. They gain more energy. What does that mean? That means there is an increase in the collision frequency of what? Collision. Not only just the frequency of collisions. The collisions are more effective. What do we mean effective? They are big enough to cause a reaction. Okay, they have more energy, they collide more, and they collide with more energy. Okay, remember we say rate of reaction depends on two things: frequency of collision and the energy of collision. Temperature will increase the frequency of collision, and temperature will also increase the energy of collision. So a higher temperature, if they are high enough, we have much more um, successful collision, or we say effective collision, when the energy is high enough. Let's look at an illustration of this. Now we're going to look at how much of a reaction takes place in low temperature and how much takes place in high temperature. Now take note of the number of collisions here. Okay, we have a counter that counts the number of collisions at high temperature, and also a counter that will count the number of collisions at low temperature. This will happen in 50 seconds. So we start now. Time is going. You can see collisions are counted. Each collision 5, 4, 3, 2, 1, 0. Now this clearly explains it. This was faster and they had more energy, and we saw much more collision, 154 collisions at high temperature and 67 collisions at low temperature. This will definitely be a faster reaction. Okay, faster reaction. The reaction will definitely be faster at lower temperature. Take note, there are equal number of particles, right? Equal number of particles, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Equal number of particles, but we had much more collisions because they were faster, they had more energy, there was more collision. Okay, why batteries are some of the applications. Okay, batteries are more likely to run down in cold weathers, okay, right, than in high weather. How does temperature affect the rate of reaction? We see another reaction here where we use sodium thiosulfate, hydrochloric acid, and it gives us sodium chloride, sulfur dioxide, and sulfur, which is yellowish in color, cloudy, and then water. Okay, so this particular reaction here, right here, with sodium thiosulfate, interesting reaction, shows us a color change when this reaction happens. Something we do regularly in the lab when we study rates of reaction. Okay, and we mostly see the change in color because of the production of sulfur, which makes the reaction cloudy. Now, in doing this reaction, what we do is we change the temperature each time and then measure how fast each reaction takes place. Right, that gives us an idea. Practical guide important. Please take note of this. Gives us an idea of, we call this the disappearing cross experiment. We'll look at it more. We'll look at it more. Disappearing cross experiment. So this is able to tell us how fast the reaction happens because the reaction becomes cloudy and the cross disappears. Okay, let's look at the simulation of the reaction right here. So sodium thiosulfate, hydrochloric acid, we use it to investigate the effect of temperature. So we start by drawing a cross on a sheet of paper, and then we place our reactant mixture, conical flask, on top of the reaction. Okay, in this case we're using a dish. Now you see here that we can see the cross, right? Now when it gets to a point that this reaction becomes cloudy, the cross disappears. We no longer see the cross, and then we stop our timer. That tells us that the reaction is complete. So we do this at low temperature, we do this at high temperature, and it shows us the time it takes for this reaction to happen as we change the temperature. So next thing, we place our reactants and then we start our timer. Okay, you can see it disappears. But we'll stop our timer. Okay, we can no longer see the cross. It has disappeared because it turned cloudy. Okay, and that took about 46.8 seconds rather. took off 40 points. Okay, so 100. Yeah. So this was done at different temperatures, and this is the result we that was gotten. We see here that at 25 degrees Celsius, it took a longer time. Uh, Temperature increased, became shorter, smaller time, shorter time. As temperature was increasing, that we saw that that cross disappeared in lesser time. Now, when we plot this in the graph, we have our reaction, our rate of reaction graph. Now, in this case, we have time here, which is why we have time here, because our time in this case is our dependent variable. Okay, remember we changed the temperature. Temperature is what we change, which is our independent variable, and this is what is changed by our independent variable. So this is our graph that we get here. We see that the reaction rate approximately doubles for every 10 degrees Celsius. So if we do the rate of reaction here at this temperature, and then we do it at this temperature, right? Change in temperature over time, right? Change in the rate of reaction at this point, rate of reaction, change in concentration per time, do it at this point for every 10 seconds, we would see that this reaction, rate of reaction, doubles at each of these points. We see that in the table.